So, having looked at cases involving friction, now let's look at case involving motion in a lift. If we are looking at a case involving motion in a lift, I think we should be having some idea about what a lift is, that is used to, should I call it a system that is used in this storied building, those tall buildings, to move from one level to another, other than the staircase for going up the upper rooms or moving downward. So the lift transports people in those tall buildings from one level to another. So it operates electrically. So we are now going to analyze the motion of bodies in a lift, but still looking at the idea of now here we shall be bringing some idea of the second law of motion. So let's begin with looking at a body moving upward. So I can say, consider a body of mass m kilogram accelerating upward accelerating at a rate of a meters per second upward as shown below. Okay, supposing I consider a body of mass m kilogram in a lift, and we shall be neglecting the weight of the lift. So if I have this as my lift, okay, maybe let me consider that body to be maybe a man of that kind of weight, okay, in a lift. We said we are looking at the lift going upward with acceleration a. Therefore, this guy here, his weight will be acting as mg, okay, and then we'll be having a normal reaction R. So what will be true is that we shall be using Fr equaling to ma, force the direction of motion, minus force opposing motion equaling to ma. So if the body is moving up, the force in the direction of motion is the normal reaction R, isn't it? Minus force opposing motion will be the weight. As it's moving up, the weight is pulling down. So equaling to M minus mg should be equaling to MO A. And now from here we can say comfortably that R will be equaling to MA plus MG. Okay? That is the expression for normal reaction. And please don't forget that normal reaction that we exert in the lift is equivalent to our weight when the lift is in motion, or even if it is not in motion. But the point is normal reaction, either it is in motion or downward or upward or stationary, normal reaction is always equaling to the weight of the body in its state, either state of rest or state of. So supposing you enter in a lift with maybe say a weighing scale, you want to weigh yourself. The weight you get, if it is moving and then you try seeing maybe the one you stand on, the weight you read is equivalent to the normal reaction. So normal reaction is the weight of the body. So if the lift is not moving, that would mean that from our idea of R equaling to MA plus MG. Okay? If the lift is not moving, that means this component is 0 and R will be equaling to M, and this is basically true for bodies which are at rest. But should the body begin moving, the normal reaction will be given by this expression now. And you realize that now this is bigger than when the body is at rest. Because they're saying if the body is at rest, normal reaction is mg. But should it start moving, it is now mg plus ma. What does that mean? That when a body is moving up, it becomes more heavier than when it is at rest. Okay? After knowing that normal reaction is always equivalent to the weight of the body in its state, either of motion or at a rest. And then let's look at case 2. A body moving downward. Downward. If the body accelerates at a rate of a meters per second downward, then what is very true is that if I now have this guy here in his car lift, something like that, and now he has his weight here mg, he still has normal reaction because as he's standing, the lift will be supporting him. And if you are looking at the lift moving down at that rate a, we shall say also, using this equation here, Fr equaling to ma, okay? We shall say force in the direction of motion. Now it is moving down. The force in the direction of motion minus the force opposing motion should be equaling to ma, and the R will be equaling to mg minus ma, okay? And that alone tells us that when the body is moving downward, its weight reduces. Because you can compare these two. This was mg plus. That means that here we are maximizing by adding. Therefore, the body is more heavier when moving upward. But here we are minimizing, subtracting away. So that means that the body will experience some loss in weight when it is moving downward. And it is important that you should note that if the body is at rest, R will be equaling to mg, which is the actual weight of the what? That if the body is at rest, and then you go and stand on the weighing scale, the weight you read is your real weight, which is the normal reaction at that time, which will be mg. But should you weigh yourself when you're moving upward? If you're someone of 70, you can even go up to some value depending on the acceleration, isn't it? But the truth is your value will appear bigger than what you have. That is when it's moving up. And should it start moving downward, someone of 70, your weight will look like it has reduced. And all those weights are given by the normal reaction of the body. And please, you should also note this one practically in life. We always say the acceleration of a body in a lift should always not be equaling to the one due to gravity. G should never be equaling to the rate at which a body is going to move down should not be equivalent to 9.8. The moment is equaling to that, that means the body will experience, should I call it weightlessness? In other words, there will be no reaction. Because if G equaling to A, that means that reaction is equaling to 0. If you pick to and bring here, if G equaling to A, that means you will say R equaling to mg minus mu if A is now equaling to that. So that means R is equaling to, and if there is no normal reaction, it means that you're moving down, but the reality is that your leg is no longer in contact with the lift. That means that it is like you are falling freely from up. So it is really very, very dangerous. So for the design of lift, it is always encouraged that A should be less than G, or should not reach non-point A. Otherwise, the body will experience what we're calling weightlessness, or a scenario where the body exerts no reaction to the support that is supporting it. So let's now meet for our example in the next episode.